Alright, let's continue section 2.3, Analyzing Limits. Have a little more fun here, and we're going to come up with a strategy for finding limits. On the previous 3 pages, you studied several types of functions whose limits can be evaluated by direct substitution. This knowledge, together with the following theorem, can be used to develop a strategy for finding limits. A proof of the theorem is given in Appendix A. So, Theorem 1.7 is about functions that agree at all points except one. So we let c be a real number, and we let f of x be equal to g of x for all x values except this one point c in an open interval that contains point c. If the limit of g of x as x approaches that c value, then the limit of f of x also exists and the limits are equal. The limit of f of x is equal to the limit of g of x at that point c. Let's look back here. We saw this example, I think it was in the last section when I think we made a table of this one if I'm not mistaken, and we figured out what the limit was as we got really close to an x value of 1. And you know, we did that with a table, and I think we did graph it afterwards. It looked like a parabola with a hole in it right above our x value of 1. And there's an easier way to find that limit without constructing a table or having to rely on a graph. And the easiest way to do that is to look for something that you can factor out and cancel. So, this is a cube minus a cube, a difference of cubes, and that is factorable. This goes way back to pre-calc. Oops. So when we factor this difference of cubes, our first factor is going to be a binomial. This is x to the third, so the first term is x. The cube root of 1 is 1. And that sign will be the same. Here it's a minus, here it's a minus. Now in the second set of parentheses is a trinomial. The first term is this term squared, x squared. The last term is this one squared, negative 1 squared is 1. And in the middle, that's a plus 1. This is a minus sign, so the signs always flip. This will be a plus, and this middle term is these two multiplied together. 1 times x is x. Now our denominator is going to stay the same, x minus 1. And here now we see we have this common term in the numerator and denominator, so we can cancel it out. So I'm going to rewrite the original function we started with. The limit as x approaches 1 of x cubed minus 1 divided by x minus 1 is exactly the same as the limit as x approaches 1 of this polynomial, x squared plus x plus 1. This in the theorem they said that the limits of the two different functions are equal as we approach that c. The limit of f of x is equal to the limit of g of x. That's what's going on here. These functions are the same when it comes to the graph and the number as we approach 1. Remember when we did this in the previous section, the first thing we tried to do was direct substitution. If we plugged that 1 in for this x and for this x, we got that form of 0 divided by 0, which is going to cause us a little bit of trouble. So we come up with a way to factor part of that numerator, and then we divided something out, so we no longer have a divide by 0 scenario. So direct substitution would not work on this problem at the very beginning, but now that we've factored it and canceled out a common factor, we can now try direct substitution again. Let's plug this 1 in for the x's, so we're going to have 1 squared plus 1, which is equal to 3. And that's the exact same limit we found using the table or the graph, however we did it before. Now graphically, what did we just do here? Get to the next slide. The original function, x to the third minus 1 divided by quantity x minus 1. When we graphed that, it was a parabola. And you can always look at your highest power in the numerator and denominator. Highest power in the numerator is x to the third, highest in the denominator is x to the first. You divide those, you get x squared. See, no matter what happens afterwards, this is going to define the basic shape of the graph. So we have a parabola opening up. But we had that hole in the graph above x is 1. That's where we were undefined, because if we plugged 1 in right here, we get our divide by 0 scenario. But we took this function here and we factored the numerator and we canceled common terms, and if we graph x squared plus x plus 1, we now have the same parabolic curve opening up, but the only difference is where there was a hole in the original function, when we factored it and canceled the common factors, we sort of paved over that hole. This polynomial function does not have a hole in the graph above x equals 1. And I recopied the theorem 1.7 here again. You know, the limit as x approaches c of each function, f of x and g of x, are the same because they're the same everywhere else. Here at -1, we're on this point of the graph. At -1, we're on the exact same point. At 0, we're crossing the y-axis at 1. At x is 0, we're crossing the axis at 1. Every point on each graph has a corresponding point on the other. But where we ran into trouble, where this hole exists and this function is undefined, this function does not have that hole. It behaves the exact same everywhere else on the graph, so that's telling us that this limit is exactly the same as this one. So here's our strategy for finding limits. Learn to recognize the limits that can be evaluated by direct substitution. Those are our first 6 theorems. Always try direct substitution first. If the limit of the function as x approaches c cannot be evaluated by direct substitution, try to find a function, another function g, that agrees with the f function for all x values other than the one that we're worried about. And choose g such the limit of g can be evaluated by direct substitution. You know, factor it, simplify to get that divide by 0 scenario to disappear. Number 3, apply that theorem 1.7 to conclude analytically. You know, when we factor and cancel, we just try direct substitution again, and we find our limit. And as a fallback strategy, or to reinforce an answer that we found above, we can use a graph or a table to figure out that limit. So let's try a couple examples here. We're going to try dividing out and a rationalizing technique. 2 techniques for finding limits analytically are in these next 2 examples, 7 and 8. The dividing out technique involves dividing out common factors, and the rationalizing technique involves rationalizing the numerator of a fractional expression. Now here in example 7, we have this limit as x approaches -3 of this polynomial. We're going to try direct substitution. I'm going to plug, you know, we might as well not even plug it in the numerator. Let's see what happens in the denominator first. We plug a -3 in here, we're going to get -3 plus 3 is 0. So that right there we know we're going to have problems with. Let's just check out that numerator though. We plug a -3 in there. -3 squared is +9. Plus a -3 would take us to 6, and 6 minus 6 is 0. I think we get to it later in this section. This is called indeterminate form. D-E-T-E-R-N. Indeterminate form. 0 divided by 0 is a bad thing to see. So we cannot just do direct substitution here. We're going to try to simplify this if possible. So our limit as x approaches -3. And you know, with these types of problems, there's built-in clues. If we're going to have something cancel in the numerator and denominator, our denominator is already just this binomial, x plus 3. So if we're going to factor the numerator, hopefully one of our factors will be x plus 3. So we want to factor this numerator. Leading term is x squared, so we have to have an x and an x as our first term in each binomial. The -6, the factors of -6 that add up to +1 are +3 and -2. Again, I did have a clue of that by the x plus 3 in the denominator. So now these are going to cancel out. And our original limit is going to be equal to the limit as x approaches -3. Again, these canceled out, so we're just left with x minus 2. Direct substitution did not work in the original problem, but now it's going to work. Plug that -3 in, we get -3 minus 2, which of course is -5. That's our limit as we approach -3 of that original function. Let's see here. The original functions here in the blue box. Looking at just those highest powered terms, we have an x squared divided by an x. If we divide those out, we get x to the first power, and first power functions are linear. So x squared plus x minus 6 divided by the quantity x plus 3, that is going to divide out to just be a line. In the example, direct substitution produced the meaningless fractional form 0 divided by 0. An expression such as 0 divided by 0 is called indeterminate form, because you cannot, from the form alone, determine the limit. When you try to evaluate the limit and encounter this form, remember that you must rewrite the fraction so that the new denominator does not have 0 as its limit. One way to do this is to divide out like factors, as shown in example 7. A second way is to rationalize the numerator, like we're going to see in the next example. And back to here, when we did divide that out, we were left with the line x minus 2. F of x equals x minus 2. So if we graph this function, our original function, it is a line, but we have that nasty hole in it right below the x value of -3. But we factored the numerator, canceled out like terms, and we're left with this. Y equals 1x minus 2. If we were to graph that line, our y-intercept is -2, and our slope is +1. So the graph of this line would lie right atop of the graph that we already have, and more than that, it's going to pave over the hole in the graph that was caused here by a -3. Alright, and another technique to try is this rationalizing technique. We have our limit as x approaches 0. Our numerator is square root of the quantity x plus 1 minus 1, and all divided by x. So first, direct substitution. We plug in a 0 for x, we get the root of 1 minus 1 divided by 0, or 0 divided by 0. So that's our indeterminate form. We're going to have to work a little bit harder to find this limit. So how do we rationalize the limit as x approaches 0? I'm just copying the original function here. Divided by x. I can multiply any fraction by 1 and not change it at all. And the key here I want to do is try to get rid of this radical. So I'm going to multiply by the conjugate. I'm going to multiply the numerator by root of x plus 1 quantity plus 1. Just those signs are different. And if I multiply the numerator by that, I got to be fair and multiply the denominator by that also. So let's see what happens when we multiply. We have a sum and a difference of terms. So when we FOIL that out, the middle terms will cancel, and here we'll have root of x plus 1 times root of x plus 1, which is x plus 1. We're multiplying it by itself, we're squaring it so it eliminates the radical. And then we have minus 1 times 1 is 1. In the denominator, I'm not going to distribute yet, because usually you'll see something neat happens here. I have this x times this denominator as a quantity. Root of x plus 1 quantity plus 1, close parenthesis. Now look what happens in that numerator. We have x plus 1 minus 1. So what we're left with is just x. In the denominator, we have x times a quantity. Root of x plus 1 plus 1. And the reason I didn't distribute that shows up right here. Now we can cancel these out. And remember, when the numerator is completely canceled here, there is a 1 left in there as a placeholder. Guess I can get rid of this. And then we're going to be left with the limit as x approaches 0 of 1 divided by x plus 1 square rooted, that quantity plus 1. In the original problem, direct substitution with the 0 did not work, indeterminate form. Now it will work. Plug that 0 in for x. So we have 1 over. That's going to be the root of 0 plus 1, or the root of 1, which is 1, plus 1. And we get 1 divided by 2, 1/2. Limit is 1/2. And we can always back that up with a graph. If you were to throw that into the old graphing calculator, the original function would look like this, but we would have a hole right above the origin. When we rationalized our numerator, we get a different function, this 1 over this quantity, which looks exactly the same graphically, except when we rationalized, we paved over the hole. So that limit is the limit as we approach 0 from either side. We're approaching the y-axis. If we're on the graph, we're sliding down towards a height here on the y-axis of 1/2. And if the graph's not good enough, we can also bust out the table. You can put that in the old TI-89. So we put the function into the y editor, we go to the table and start plugging in different x values, getting closer and closer to 0. As we approach 0 from the right, our function is approaching 0.5. As we approach 0 from the left, the function is still approaching 0.5. Since it's the same on each side, we know the limit exists, and it is 1/2. And that's probably a good spot to end this video. Next, we'll pick up with the squeeze theorem. We'll prove that, and then there's just a couple more examples, and that will be the end of 2-3.